mention real briefly, but the vector that points down the x-axis is one of the standard basis vectors. The vector that points down the y-axis with length 1 is another of the standard basis vectors, and the vector of length 1 that points down the z-axis is one of the standard basis vectors. And again, I know this is Cal 3 and it's not linear algebra, but in linear algebra we're learning about spanning spaces. You could cover all of R3. You could find every point in three-dimensional space by using these three vectors. Just multiply this one by some number, multiply this one by some number, multiply this one by some number, add those three together, you found a point out in space. Change your multiples, add those together, you found a different point in space. So these will span all of R3 by taking some number times I and adding it to some number times j and adding it to some number times k. And, by changing a, b, and c, you can find all points in R3. That's what it means by spanning all of R3. You could go from the origin to any point in R3 using those. So that's what's kind of meant by standard basis. You could build all of R3 with these three.
And we've already, again, it says then use the idea of standard basis to rewrite the vector found in 3. Actually, we've found 2 vectors in 3, but we've done this before. I mean, I kind of just automatically do it. This is called the component form of a vector, but the I, J, K form, or the standard basis form, would be to take each of these coefficients and have them multiply I, J, and K. Okay, so they're just two synonymous ways to write vectors. And to me, I look at those and I read the exact same thing. Sometimes, depending on what you're doing, the IJK form might be, like, for example, if you're doing cross product, to kind of help set up your cross product, you use IJK. But otherwise, there's usually not a reason why you want to write it one way or another. It's just you need to be able to read both of them and understand they're both expressing the same thing. Okay, number 5. Let's do number 5, and then we'll take a little break. Okay. Number 5 wants us to create a vector that has length 6, but points in a specific direction. So what we're going to do first is we're going to find the unit vector for our vector given, okay? So we're given the vector -2, 4, 2, find its unit vector. So the length of it would be the square root of 4 plus 16 plus 4. So that's what, the square root of 24. And actually, because these are all even, it might be helpful for us to recognize that that is 2 root 6. So my unit vector will then be -2 over 2 root 6, 4 over 2 root 6, 2 over 2 root 6,
so that's my unit vector. That vector has length 1. It doesn't have length 6. I want a vector that points in the same direction as this vector. Well, this vector points in that same direction, but it has length 1. So what I can do, though, is I can multiply my unit vector by the length that I want. So if I multiply those components by 6, I will have a vector, I will have a vector that has length 6, but points in the same direction as the two, the original vector and its unit vector. If you're unconvinced that that has length 6, you could always test it. So square -6 over the square root of 36, you get this. Square 12 over the square root of 6, and you get that number. Square 6 over the square root of 30, square root of 6, and you get this number. So 36 plus 36 is 72. 72 plus 144 is 218. Wait, no. 216.
Would it be okay to simplify those fractions to, I believe it would be 6, 24 plus 6?
Yes, I agree with you, it would. But since I already have this written on the board, I'll just leave it.
Fair enough.
But yes, I agree, yes, this is 6, this is 24, this is 6, so 12 plus 24 is 36, and you get something else, yes, I agree. Okay, so it has length 6. If I did graph this and I graphed that, I would, on my, my applet, I would see them pointing in the same direction